when trying to understand the health of a complex machine just by listening to its hum. Vibration analysis is that ear, powered by science and engineering. At its core lie two foundational concepts: sampling and resolution. Mastering these means unlocking the full diagnostic power of modern vibration analysis tools. Every signal, from a rotating shaft to a gearbox, exists in a continuous world, flowing smoothly with infinite detail. Instruments capture only snapshots, sampling the vibration at precise intervals. Sampling is the bridge between the analog world and the digital realm where analysis becomes possible. Why is sampling rate so critical? Imagine taking photographs of a spinning fan blade. If you snap images too slowly, you'll miss the blur, the nuances invisible between your shutter clicks. In vibration analysis, sampling too slowly lets frequencies slip past undetected. This is called aliasing, where signals masquerade as lower frequencies, giving misleading information. The solution lies with the Nyquist theorem. Always sample at least twice as fast as the highest frequency you want to analyze. For example, to capture signals up to 5,000 Hz, your sampling rate must be at least 10,000 samples per second. Higher rates provide better fidelity, but require handling more data. Now, let's turn to resolution. Resolution determines how finely we can distinguish closely spaced frequencies within our sampled data. It's like the difference between hearing a single out-of-tune piano string or a whole orchestra with each instrument distinct. Better resolution means spotting subtle defects sooner and more confidently. Resolution depends on two factors: the range captured and the number of lines in the spectrum, often called FFT lines of resolution. The frequency range extends from 0 up to half of the sampling rate, the famous Nyquist frequency. FFT lines define how many slices the spectrum is split into. More lines mean you can dissect the signal's details more closely, but also require more computational power. When configuring a vibration data collector, you must select a sampling rate and the number of spectrum lines. Set the sampling rate too low, and you risk missing defects. Choose too few lines of resolution, and peaks from different sources blur together, masking important information. Consider monitoring a rolling element bearing. Faults often reveal themselves as high-frequency spikes, sometimes masked by other vibrations. Without an adequate sampling rate, these spikes might disappear, and the diagnosis could be missed. Insufficient resolution might cause fault frequencies to overlap with background machine noise. But there's a balance. Higher sampling rates and more lines of resolution demand more memory and processing time. For portable route-based measurements, operators must optimize settings to maximize diagnostic value without overwhelming the system. Let's review some best practices. Always check the highest frequency of interest for your application. This determines the minimum sampling rate. Select enough lines of resolution to differentiate between expected fault frequencies, such as bearing tones versus gear mesh frequencies. Use anti-aliasing filters to prevent unwanted signals from contaminating your data. Understand your equipment's memory and processor limits. Optimize settings for clarity and practicality. Advanced systems may include auto-configuration tools or recommended presets based on typical machinery, but an informed analyst adjusts values for unique frequencies and diagnostic goals. Practice using your tools and review spectra for signs of insufficient sampling or low resolution, such as unexpected peaks, blurred features, or missing patterns. A deep comprehension of sampling and resolution empowers you to extract truth from complex machinery, detect faults earlier, and protect your operations from unexpected failures. Sampling and resolution are not just settings, they are the foundation of class-leading vibration analysis. The more precisely you measure, the more confidently you can act. Apply what you've learned the next time you set up a data collector or interpret a spectrum. Precision begins with understanding, the kind you now possess.